Okay, so today we're going to be doing notes on section 7.2, properties of the probability of an event. So looking at the top of your notes, students should be able to find the probability of an event, find the probability of E or F when E and F are mutually exclusive, use the additive rule, find the probability of the complement of an event, use a Venn diagram to find probabilities, and at the very end we're going to compute odds. So looking first of all at this first box, two or more events of a sample space S are said to be mutually exclusive if and only if they have no points in common, and that's known as disjoint. Whoops. So if I'm going to look at a Venn diagram of what that looks like, here's my little rectangle. Those two circles do not intersect. So that's an example of mutually exclusive. Okay, here's an example one. In tossing two fair dice, are the events the sum of 6 and the sum of 8 mutually exclusive? And can you get, when you roll two die or when you add two numbers together, can you get 6 and 8 happening at the same time? And no, you cannot. So yes, we would say these are mutually exclusive because we cannot get 6, the sum of 6 and the sum of 8 at the same time. Okay, at the same time. So that's what mutually exclusive means. You cannot have something happening at the same time. What is the probability of obtaining a sum of 6 or a sum of 8? Okay, so let's let A be equal to the sum being 6. Let's let B be equal to the sum of 8. Okay, so when I think about this happening at the same time, go back to the big chart on the previous notes of we had rolling two die and count up the number of times that you can get the sum of 6. Well, I see that that happened 5 times out of 36. And also count up the probability of getting or count up the number of times that we got an 8, a sum of the two die to be 8. And if you look at that chart, I got that to happen 5 out of 36 times as well. Okay, so when I think about that, what's the probability of getting a sum of 6 or a sum of 8? And I'm going to be using that additive rule. The probability of A union B would be the probability of A plus the probability of B minus when it happens at the same time. Okay. So when I think about that, the probability of A would be 5 out of 5 out of 36 plus 5 out of 36 for the probability of B. So I get this to happen 10 out of 36 times. It's not going to happen both at the same time, so I really don't need to subtract that. Okay. So if you think about this, every time it's mutually exclusive, I don't really have to think about subtracting the probability of A minus B. Now, I'll be very honest with you, I'm not going to memorize that formula I just highlighted. But do notice that when it's mutually exclusive, the intersection in E and F is the null set. And let's go back and let's highlight mutually exclusive, nothing in common, or disjoint. Those are some terms that are very important to be familiar with. The additive rule can be used in probabilities. I actually was using it in that first example, but it's very similar to what we've had before when we did the number of items. The probability of E union F is a probability of E plus a probability of F minus the intersection of E intersecting F. Okay, so let's do an example using probably that probability, the additive rule for probability. Jenny is taking courses in both mathematics and English. She estimates her probability of passing mathematics at 0.4. So let's write that down. Probability of passing math is 0.4. That's not very high. And the probability of passing English is 0.6. She estimates her probability of passing at least one of them is 0.8. Now, it's real important that you understand that the probability of at least one of them is actually the probability of math or English. So that's one or the other or both, and that's 0.8. What is the probability of passing both courses? So I'm going to think about my additive rule here. I'm going to do the probability of math or English is equal to probability of math plus the probability of English minus when they happen at the same time. Okay, so plugging in what I know here, I have a 0.8. Probability of passing math is 0.4. English is 0.6 minus, I don't know this one right here, probability of math and English happening at the same time. So that's passing both of those. So I can do my algebra. I'm going to move this probability here to the other side. Probability of passing math and English both at the same time is going to be basically 0.2. Okay, there it is. Moving on to the next one. After midterm exams, Jenny reassesses her probability of passing mathematics to 0.7. Yay, she increased her math probability here. She feels her probability of passing at least one of these courses is still 0.8. Okay, so let me go back and write this out. The probability of passing math now is 0.7. She feels the probability of at least one of these courses is still 0.8, so that's a probability of math or English is still 0.8. But she has a probability of only 0.1 of passing both of those classes. Ooh, that's bad news. Math and English is 0.1. If her probability of passing English is less than 0.4, she will drop English. So we got to figure that probability out. So, you know, keep in mind you can also, instead of using the additive rule, you can also use Venn diagrams. So it might be helpful, I don't know, to do this one with Venn diagrams. Here's math and English. Let's see if we can do it that way. So both of them is 0.1, so that's going to go in the middle. Math is 0.7, so this is going to be 0.6. All of them, oh, I can't see that. I got to start over again. Let me erase that. Okay. Make this a little bit bigger. Okay, so here's my math on the left, English on the right. I'll do fill in the color with purple. 0.1 goes in the middle. Math is 0.7. I've already got 0.1, so this is 0.6. And then math or English, remember that's one or the other or both is 0.8. So those three, that interior right there has to add up to be 0.8. So when I talk about that interior, I'll highlight it. All this has to add up to be 0.8. So I'm going to take 0.8 minus, so far I've got 0.7. So that's a 0.1. Everything has to add up to be 1. So I got 6, 7, 8. So on the outside I get 0.2. What was I trying to find here? Her probability of English. Probability of English, add up all the circle for English and I get 0.2. So if I look at that, it says she's going to drop the class if the probability of passing English is less than 0.4. So we're going to tell her she better drop the class. Okay, so you have a choice of doing your probabilities. You can use your additive rule or you can use your Venn diagram. So that's still a possibility. Okay, I know we talked about probabilities in our last lesson, but this is just a nice little summary here in this box. So the probability of your events have to be between 0 and 1. For number 2, the probability of something not happening is 0 or all the events is 1. Here's our additive rule for number 3. Number 4, the complement. If not E is a complement of E, the probability of not E is 1 minus the probability of E. We'll talk about that more today. If an experiment has n equally likely outcomes, okay, so if we have equally likely outcomes, here we have a probability of the number of ways something can happen over its total sample space. So there it is, just a nice little summary. Looking at the review here, what I'd like for you to do is have the sub pause, and I would like for you and your partner to go through number 4 together. So go ahead and pause the video so you and your partner can do number 4. Okay, just checking our answers on number 4. I got 8 over 23, 5 over 23 for part B, 15 over 23 for part C, and 16 over 23 for part D. When it says red or white or blue, looking at part D, I add up my red, my white, and my blues, which are 16, and I divide it by the total. So a lot of times when you're doing these, you might want to put, what is my total up here? Total is 23. Okay, moving on to example 5. Oh, by the way, if you have any questions on that, why don't you take a couple minutes and make sure everybody in the room understands those problems and that you've got those right. Okay, example 5. Here's something else. Through observations, it has been determined that the probability for a given number of people waiting in line at a particular checkout register of a supermarket is as shown in the table. And you can see the table here. Find the probability of at most 2 people in line. At most 2 people in line means I'm going to have either 0, 1, or 2 people in line. So I'm going to look at this. I'm going to add my probability of 0 people in line, which is 0.1, the probability of 1 person in line, and the probability of 2 people in line. So the probabilities are already given to us, so we can just go ahead and add those together. 0.45. What's the probability at least 2 people in line? At least 2 people in line means 2, 3, or more. So the probability of 2 people in line is 0.2, 3 people in line 0.24, and then it has 4 or more, so that's 0.31. So that is 0.75. And then it has at least 1 person in line. So that would be, that at least 1 person in line would be 1, 2, 3, 4 or more. So I could be adding these 4 numbers together. Now let's do our complement. Couldn't I do 1 minus what I don't want? I don't want 0 people in line. So I could possibly think about that complement rule that we talked about earlier. So I'd have 1 minus 0.1, which is 0.9. And if you add these 4 numbers together here, 0.15, 0.2, 0.24, 0.31, you will get 0.9. So it doesn't matter which way you do it. Okay, looking at example 6, it says, in an election, 2 amendments are proposed. The results indicate that of 850 people eligible to cast a ballot, 480 voted in favor of Amendment 1, 390 voted for Amendment 2, and 120 voted for both, and 100 approved neither. So I'm going to first of all do a Venn diagram because I'm just feeling these numbers are kind of here for a reason. I need to get them organized. Amendment 1, Amendment 2. Okay. I always start with what's in both, and it told me 120 were in both. So I'm going to put 120 there. It said that for Amendment 1, 390 were in favor of Amendment 1. Well, I'm going to, wait, no, that's Amendment 2. 390 voted for Amendment 2, so I'm going to take 390 and I'm going to subtract my 120 so I can see that I have 270 that goes over here. Remember, the whole circle has to add up to 390. Amendment 1 was 480. So I take my 480 and I'm going to subtract my 120 to see that I get 360 for that one. Okay. So then it said that 100 approved of none of these, so that 100 goes on the outside. Well, okay, so what am I trying to find in part A? The voter is in favor of 1, but not 2. So that would be something that looks like 1, but not 2. Gosh, that looks kind of weird. Okay, so that would be 360 out of my total, which is 850. And keep in mind, you do not have to reduce fractions. You can leave them like that. Part B, the voters in favor 2 but not 1, very similar. 2 intersecting not 1. Whoops, 2 but not 1. That would be 270 over my 850 total. Okay? And again, don't even bother to reduce. You can leave it like that. Well, we all can see, though, that the zeros cancel out. We can at least go 27 over 85 and 36 over 85. we could at least do that and not take away from the time needed to take an assessment. Okay, next one. Here's where we start talking about odds. Often the probability of an event can be expressed as odds, either odds for an event or odds against the event. So odds for the event are the probability of E over the probability of not E. And the odds against it, the probability of E over the probability of, or not E over the probability of E. I'm going to probably not quite do it this way. Here's one way you can work the problem. For the odds for E that are A to B, the probability of E would be A over A plus B. The odds against it would be B over A plus B. And sometimes it just gets a little confusing. So I'm going to write it like this. Odds. Odds is successes, failures. Or you can write it successes over failures. That's how I'm going to think of odds. The number of times it happens versus the number of times it doesn't happen. And then we'll have to kind of think about that in reverse if they want the odds of it not happening. Okay. The other thing you have to remember is that probability. When we do probability, remember that was always successes, or the number of times it happened, over the total. So just kind of keep this straight. Odds is successes to failures. Probability is successes to total. Now odds, I don't care if you put them in fractions or put the little colon in between them. I really don't care. Okay, so let's look at this one. Example 7. It has been estimated that in 70% of the fatal accidents involving two cars, at least one of the drivers is drunk. If you hear of a two-car fatal accident, what odds should you give a friend for the event that at least one of the drivers was drunk? So if I think about this, 70%, the probability of a fatal accident, at least one of the drivers is drunk. So the probability at least one of the drivers is drunk, the probability is 70%, 0.7. Well, we know that that's the same as 7 over 10. Okay, that means out of 10 times, 7 times it happened. How many times did it not happen? Well, that means that 3 times it did not happen. So this would be my odds. At least one of the drivers was drunk. 7 times it happened, 3 times it did not happen. So that would be 7 over 3. Doesn't matter which way you do it. Okay. So I always kind of think about the probability and say, okay, out of 10 times, 7 times it had to happen. That means 3 times it did not happen. So let's look at example 8. If in repeated rolls of 2 fair dice, the odds for rolling a 5 before rolling a 7 are 2 to 3. What's the probability of rolling a 5 before rolling a 7? So it's given me the odds this time. Odds are 2 to 3. 2 times it happens, 3 times it did not. So you have to add them up. What's the total number of times that we're talking about? The total is 5. Okay, so the probability, what is the probability of rolling a 5 before a 7 would be the number of times it happens, which it happens twice, out of the total, which is 5. So my probability is 2/5. There we go. Okay, so here we go. Here's another one. It says, suppose E and F are two events. I have the probability of E being 0.25, F is 0.45, and the intersection is 0.1. Construct a Venn diagram. So let's do that first of all out here. I have two events, E and F. Again, remember our Venn diagrams, we start with the intersection. They both have 0.1. So the probability E is 0.25. I've already got 0.1, so this is 0.15. And F is going to be that little space is 0.35. Add those up, subtract from 1, so my outside is going to be 0.4. In your probability Venn diagrams, everything should add up to be 1. Find the probability of neither E nor F occurring. So that probability would be what's on the outside, so that's 0.4. Find the probability of E but not F occurring. Probability of E, but not F, would be 0.15. Okay, so keep in mind that yes, you can use your Venn diagrams for probabilities. I think I'm kind of a visual person, so that's what I kind of like to do as well. So if you have any questions, please be sure to get a pass to come in for SRT, and be sure to check and see what else is going on for the rest of the period. You guys have a great day.